We're going to be talking about different factors that affect solubility. We're going to start with a sort of phrase that people use about solubility, which is like dissolves like, which means that solvents that have very similar intermolecular forces to their solutes should dissolve very easily. But when they have very different intermolecular forces, they typically do not dissolve in each other. So when we think about intermolecular forces and whether or not they are similar or different, of course we have to remind ourselves of the different intermolecular forces that are present, and those are shown here. We covered those in the last chapter. And we should also, as we start thinking about this, think about the solute, which is shown with the purple spheres in the beaker at the top, and the solvent, which is the blue spheres in the second beaker down, and then we mix them together to make a solution, which of course is a homogeneous mixture of those two. We're going to think about that process in stages. The first stage, we're going to have to separate those solute particles in order to make room for the solvent, and that requires energy. So whatever intermolecular forces are present in the solute, we have to overcome those intermolecular forces to pull them apart. That's also true for the solvent, because the solute needs to fit in those spaces between the solvent particles, which means we have to separate the solvent particles as well. That also requires energy because we need to overcome whatever intermolecular forces are present. Finally, we bring the solute and the solvent together, and that is sort of the opposite process, right? Whatever intermolecular forces are present between the solute and the solvent, those interactions are going to supply energy. So when we think about the dissolution process, the first two, that first one requires energy. That's kind of an unfavorable idea. We have to put energy in, we have to put energy into the second one as well. But then the supply of energy, that's a positive, favorable thing to think about. So whether or not a solute dissolves in a solvent depends on the cost versus the payoff. So if the payoff is greater, then we end up with a soluble solute. And if the cost is too great, then they are not soluble. So that, if we go back to our like dissolves like and our intermolecular forces cartoon with these little jelly bean shapes, then remember that the intermolecular forces between the solvent particles must be broken, the intermolecular forces between the solute particles must be broken, and then the intermolecular forces that form are the ones that supply the energy that we're looking for. So this all has to do with thermodynamics. If a solute will spontaneously dissolve in a solvent, then it must have a negative delta G of dissolution. So that's a heat of solution, or that's a delta G of solution. So remember that negative delta G's are spontaneous and positive delta G's are non-spontaneous. And also remember the equation for delta G, which is delta H minus T delta S. That's shown there in the middle. This is review from last semester. You would have learned this in Chem 101. Now, if we go back and talk about, you did a lot of sort of lab work on delta H in Chem 101. You did a lab that involved taking different salts and dissolving them in water in beakers, and then you felt the test tube to decide whether or not the delta H for dissolving that salt was positive or negative, right? Does the test tube get hot? So in Chem 101 you did that lab where you identified dissolving which salts had exothermic heats of solution and which had endothermic or positive heats of solution. So remember, exothermic, the test tube got hot. And at the bottom here you're seeing what that diagram would look like. Okay, so we have a red arrow. The separation of solvent particles requires energy. Separation of solute particles, that purple, light purple arrow, also requires energy. So those arrows go up. And then the solute-solvent interactions, those supply energy, and so they're going to be going down. Okay, the energy is going to fall. So the delta H of solution for this particular example is negative, right? The arrow goes down. The enthalpy of our solution is lower than the enthalpy of our separated solute and solvent, which means that there's excess heat at the end, which is released to the surface. On the right is an endothermic dissolution where the test tube got cold. Remember, it's a similar diagram except the green arrow, the solvent-solute interactions, the ones with the smiley faces from before that supplied energy, those have a negative delta H, but it's not quite as large as the green arrow on the left, which means that the overall heat of solution is positive, right? That arrow goes up. The heat of solution, the enthalpy of the solution is larger than the enthalpy of the solute and solvent separated, which means you have to put heat in, and the heat that's required for this process to occur is absorbed from the surroundings, which is why the test tube gets cold. Now, the next statement isn't really review. You learned a little bit about this last semester, but this may be the first time we've talked about this specifically. Even salts, many salts that still have endothermic heats of solution, they still dissolve, right? So the test tube still got cold. And so remember that it can have a positive delta H but still have a negative delta G. And so if we remember why that is, that's because of entropy. Remember, delta S is a part of that equation as well. And this picture is from your book, and it is meant to show you that if you have a solute, whether it's a solid solute mixing with a liquid solvent that you see on the top, or whether it's two liquids that you're mixing together, that the entropy of the solution is always greater than the entropy of the separated solute and solvent. So entropy is always increasing as you make solutions, as you dissolve things. Dissolution processes always have a positive entropy, positive change in entropy. So if we go back to our picture here, some solutes don't dissolve at all. And that means that if we make a new picture, here I have shown you that the green arrow is way too small and our delta H of solution is way too large. So the bottom here shows you if the energy required is way, way too high, or the energy that's given back is way too low, see that green arrow is just too tiny, then it's too endothermic for delta S to overcome it. So delta S is always positive for dissolution. But if delta H is too positive, there's too large, then delta G can't become negative. A couple of other factors that affect solubility: temperature. Most solids are more soluble at higher temperature. So if you're at home and you want to make some rock candy, then you've learned that you can increase the solubility of sugar by increasing the temperature of the solvent, right? So if you heat it on the stove, more solute goes into the solution. That's true for most solutes, as you can see here. As temperature along X goes up, the solubility along Y tends to go up. That's, however, not always true for gases, right? So most gases are less soluble at high temperature than they are at low temperature, which is why when you have a carbonated drink, it will survive longer with carbonation if you put it in the refrigerator.